Alright, so today we'll be doing Chem 10 practice problems, lecture 10, and let's just get right into it. So number one is the shape of water. The sharing the electrons between the central atom and its surrounding atoms will decide the shape, aka the geometry, of the molecule. This in turn will dictate its molecular polarity, which then dictates many physical properties of the molecule. So let's do this by step. Okay, so draw the Lewis structure. It's pretty simple. So let me just do it, then I'll explain it. Now, the reason why it's drawn like that is because if you get out your periodic table, you will be knowing the valence electrons, and the valence electron is 1, 2, 3, 4, 5, 6, 7, 8. So we'll be needing the hydrogen. So hydrogen is only 1, and oxygen is only 6. So let's get out. Okay, so oxygen, we will be needing 6 of those, and hydrogen we will be needing now 2. Since oxygen does not have a little number right here, we're only gonna be needing 6. So it'll be like, even though there's nothing here, it's still 1. So 6 times 1 is 6. So since hydrogen has 2, we'll be needing but since hydrogen is 2, and if you look on the periodic table, the valence electrons are 1, like all this column is 1, you're gonna be doing 1 times 2 equals 2. Then you add the total together and you get 8. And when you write it out, this little dash right here, the little dash is considered 2. So this is 1, 2, then 1, 2, that's 4. Now, that's half of what we need. The other half, we have to find a way to put it. So like, let's say if I put one like right here, like a dash right here, that's not the proper way to do it. So what we would do is a lone pair. So 1, 2, 3, 4. Then add that all together. 1, 2, 3, 4, 5, 6, 7, 8. And that's how we will draw the Lewis structure of H2O. Now for B, how many lone pairs surrounding the central atom? So the central atom is oxygen, and the lone pairs are the little dots. So you do not count like separately, like 1, 2, 3, 4. So it's 4. It's not like that. The central atom will be just all together. So it's 2 lone pairs surrounding the central atom. Because 1, 2. Now C, how many atoms surround the central atom? Central atom is oxygen, and atoms are the little dash right here. So same thing as the lone pairs. 1, 2. Alright, so D, add your answers from B, C above. This number gives the total number of the electron groups around the central atom. Now, so add your answers by that. So what's B? We get 2, and add that, and for C is 2 equals 4. Now, if you get out your book, chapter 6, page 198, there we go, 198. Now, since we added 2 plus 2, we get 4. And to determine the electron group geometry, it's tetrahedral. I'm sorry if I mispronounced it, but that's the way I pronounce it. So it's tetrahedral. And yeah, that's the answer right there. So let me write it out. Oh. My ribbon. Tetrahedral. Okay. Based on the number of electrons groups D above and the number of attached atoms C above, my bad, around the central atom, you can predict the shape of the molecule. What is the shape of the molecule? Okay, even though it's tetrahedral, there's still two atoms attached to the side, H and O from O. So even though it is tetrahedral, it is still a bent. A bent shape is gonna be looking like, oh my bad, it'll be looking like this. This is a bent shape. And to see how it would look on the paper, it's just simply like O and H. It is just considered as a bent shape because of the two atoms on the outside. So, bent. Okay, let me just get my book out of my way. Yeah, okay. Number 2. Let's try this again with another molecule. Complete each of the following statements of the molecule of CS2. Note that C will be the central atom. Now, sometimes professors will denote saying like C will be the central atom. Sometimes other professors will say like S is the central atom. But how I remember it is usually, so like how on H2O is H2O and O has is only one of H2O out of the whole. So how right here, H2O, there's two H's and O is one. Now let's just like do it. Like let's say H was the central atom and be like you can't even write it, so it's usually the element that's just by itself. Okay, so there are blank electron groups around the central atom. So let's just write it out. Let's just do the little structure of it. Now, so you want to get your periodic table for this. So we need S over here, sulfur, carbon, sulfur. Now, how many carbons do we have? 1. So carbon, this is 4, and sulfur. So we have 2 sulfurs, and the valence electrons is 6. There we go, 6. Now, so be 2 times 6 equals 12, and you add those together, you will get 16. And how you would do it is, okay, so we have 1, 2, 3, 4. 4 out of 16. You could do 2 lone pairs up here. So let's see, 1, 2, 3, 4, 5, 6, 7, 8. 8. Now, we had to balance this out. So let's say we put a lone pair here, lone pair here. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And let's say we do another lone pair over here. 1, 2, 3, 4. So we got 4, 8, 12, 13, 14, 15, 16. You could do that, but let's just do a simpler way by erasing these lone pairs. So this is a simpler way because it is just simple and cleaner. Another one. So it'd be double. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Maybe I did it wrong. No, I did not. Did I do it wrong? Oh, my bad. I feel like I did this wrong. Did I do it wrong? I cannot do it wrong. I cannot. Oh wait, my bad. Okay, it's not in the central. My bad. Little math function. So you still include the dashes, but you include lone pairs on the atoms on the outside. So it'll be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And we got 12. 13, 14, 15, 16. That's how you would write it. Okay, so A. There are blank electron groups around the central atom. That's 2. Sulfur. 1, 2. So the electron group geometry is a linear. Now, here's a book one more time. A linear looks like this. The central atom and the 2 atoms on the side. That's how it looks like. So the number of atoms attached to the central atom is 2. Same thing as the electron over here, sulfur. Its shape of the molecule is linear. This molecule is a polar or non-polar. Now, since it has sulfur and sulfur attached to the carbon in the middle, they're basically being pulled like equally. So like it's being pulled that way, it's being pulled that way. So it is a non-polar. Now let's say there is another sulfur right here, like a sulfur right here, and it's being pulled up that way. It's being pulled up that way. So if it's being pulled up that way, it's basically being pulled upward, and that will be considered as a polar. I hope I made that clear and understandable. Okay, now on the back side, the molecular polarity. To know the polarity of the molecule, draw the shape of the molecule. Then draw in the diplodes of all bonds. Imagine a tug of war between the bonds. If they cancel out each other's pull, then there is no net dipole. So the molecule is said to be non-polar if they do not cancel out each other's pull. Then there is a net dipole, so the molecule is said to be polar. Now, show how water is polar then by drawing the dipole vectors. So let's draw that one out. Now, for water, it'd be H2O. So it'd be O. It is considered bent from, as you remember, from 1E. So it is considered apolar because they do not cancel out the pull. Why? Because oxygen is basically pulling upward. So it's gonna be my bad. It's going upward, so it's being pulled up. Now it's a little bit different from B. Now if you draw the CS2, it's gonna be looking like something like this. Now this is considered non-polar because they're basically being pulled. They're not getting like pulled out. So they're being equally pulled together. Let's say like S is pointing that way and S is pointing that way, and it'll basically rip the C in half. So it is also a nonpolar because it has the same electrical negativity values. And that is why it is nonpolar. Now, for what intermolecular force do the following molecules have? Now, if you look in your book, and turn to the page, right, more intermolecular force, ionic bonds, diplo attracts, so on and so on. So this is a page 201, chapter 6.9. Now, how you will determine its intermolecular force is from how you did it earlier, like from 3A, how it is considered a bent, or more like from 1E is considered as a bent. So if you would draw the whole intermolecular force and like trying to different like shows bent, it's gonna look like something like this. Connect that one to another O. So this is a diplo. So let me. Diplo, because of the attraction right here, it is not supposed to be being shown far away. It's just like a little dash because of this right here, of the diplo. Because it has the OH base, it can have H bonding. It also has the LDF, since all the molecules do. You need to say that. You need to say that as well. Now, since CS it's a nonpolar, you can't draw anything for that one. Like, it's nonpolar, but it only has LDF, so we just put that. CS2 is nonpolar. It only has LDF. And that concludes lecture 10 on shapes of molecules, and I'm going to redo this outro.